So, we have looked at the dyad method of synthesis for motion, path and function generation. And we started off with this equation, basically Z1 phi j minus 1 plus Z2 e power I gamma j minus 1 equal to delta j, where if delta j and gamma j are specified, then you have your motion generation problem, or if delta j and phi j are specified, then you have your path generation with prescribed timing. So, we use so for the 3 position synthesis, if you remember the table, or from these, you will have how many equations? You will have how many equations for 3 position synthesis? You will have 4 scalar equations, and so we are looking at motion generation or path generation with prescribed timing. Both have the same form. So, we have 4 scalar equations. How many unknowns? We will have 6 unknowns. The unknowns are Z1, Z2, 4 unknowns there, and depending on if it is motion generation, the unknowns would be phi 2, phi 3, path gen with prescribed timing, the unknowns are going to be gamma 2, gamma 3. Okay. So, you will have 6 unknowns, and therefore, you have 2 free choices for the 3 position problem. We have seen this before. Okay. So, the 2 free choices, we could either pick the 2 angles, make this a system of linear equations and solve for the vectors Z1 and Z2, or we could pick one of the vectors Z1 and Z2. So, instead what I am going to do now is, in general it is advantageous to me if I can specify the fixed pivot, right. When I pick Z1 or Z2, I am not directly specifying the fixed pivot, but I can rewrite this in a form where I can actually specify the fixed pivot in the plane, which as a designer may be more advantageous to me to determine this dyad. So, I just write these I am going to write these equations in a slightly different form in order to be able to specify the fixed pivots. If you remember, in the 3 position synthesis graphically, we could do that. We could specify the fixed pivots, find the moving pivot that corresponds to it, so that you can get your mechanism with the chosen fixed pivots. Okay. So, here for convenience, so since the form of the equation is based on the deltas and the gammas, my first position is sort of my reference position. So, for this case I am going to, for convenience, I am going to locate my coordinate system at the first position. So, let me take this dyad. So, I have I will just first draw the dyad in 3 positions and then we will pick the So, if this is my P1, P2, P3. This is what I want. I want to synthesize the diode that will go to these positions P1, P2, P3 with say certain orientations gamma 2, gamma 3 with respect to the first position. So, I should choose my, I will choose my origin of the coordinate system at this point P1. Otherwise, I am just going to get two known vectors. So, it is not really changing anything. So, if I do that, then if this is Z1, this is Z2, okay, and I call this R1. Minus R1 directly specifies the location of my fixed pivot with respect to the coordinate system. Okay. So, I am going to write the equations using this form. So, we are doing the case of 3 position motion generation with a specified fixed pivot. So, for convenience, I pick or I locate the origin of the coordinate system at P1. Okay. So, for 3 position motion generation, my delta 2, delta 3 which are vectors are specified. Also gamma 2 and gamma 3 are specified. So, now I have the 2 free choices. So, let me write the equations as Z1 plus Z2 equal to R1 first position. Okay. Then I can write it as Z1 e power I phi 2 plus Z2 e power I gamma 2 equal to R2, where delta 2 equal to R2 minus R1, right. So, R2 is just delta 2 plus R1. I want to specify R1, okay, the location of my fixed pivot, and then I write, because if you look here, if this is R2, then delta 2 is this is R2, then delta 2 is this equal to R2. So, this is delta 2, right, P1 to P2, that vector is delta 2. Then for the third position, I can write it as Z e power I phi 3 plus Z2 e power I gamma 3 equal to R3 and delta 3 equal to R3 minus R1. So, these are my synthesis equations. These and gamma 2, gamma 3 are specified. So, here in this set of equations, okay, the coefficients of Z2 are known and the R's are also known. Okay, that is what I am given. So, if you look at these equations, I have Okay. If I look at them as a set of equations with in Z1 and Z2. Okay, if I look at them with complex coefficients, if I look at them as a set of linear equations with complex coefficients in Z1 and Z2, then when will I have a solution? So, I have only two unknowns, I have three equations in two unknowns, right. When will this system have a solution? If I look at it as, let me just write that down, if we view the equations as a set of three complex equations that are linear and non-homogeneous, in Z1 and Z2. This set has a solution only if, what condition? You have three equations, two unknowns. So, so the two of the equations have to be linearly dependent, which means the determinant of the augmented matrix should be 0. Okay. So, only if the determinant of the augmented matrix of coefficients is identically 0. So, that means if I write the coefficients, so this becomes a condition that has to be satisfied in order for this system of equations to have a solution, right. R1, R2, R3, this determinant should be 0. Okay. So, this represents a complex. So, I know gamma 2, gamma 3, R1, R2, R3 in this. Okay. So, I can expand this as a condition on phi 2 and phi 3. So, not all values of phi 2 and phi 3 will be able to satisfy this condition. Okay. So, if I expand about the two unknowns in this equation are phi 2 and phi 3. If I expand this determinant, so I can expand it, say, about the first column because the unknowns are in that. So, I get e power I R3 e power I gamma 2 minus R2 e power I gamma 3 minus e power I phi 2. So, I am expanding about the first column. I have R3 minus R1 e power I gamma 3 plus e power I phi 3 into R2 minus R1 e power I gamma 2. This is equal to 0. So, this represents a condition that phi 2 and phi 3 have to satisfy in order for this system of equations to have a solution. Okay. So, my phi 2 and phi 3 should be chosen such that they satisfy this equation in order for me to find a solution for Z1 and Z2 that satisfy those three equations. So, I can write this in the form d1 plus d2 e power I phi 2 plus d3 e power I phi 3 equal to 0, where d1 equals r3 e power I gamma 2 minus r2 e power I gamma 3, d2 equals minus of r3 minus r1 e power I gamma 3, and d3 equals r2 minus r1 e power I gamma 2. Okay. Now, because r1, r2, r3 all are given and gamma 2, gamma 3 all these are known quantities. Okay. d1, d2 and d3 are known vectors in this compatibility equation. Now, this equation if you look at it, it is a transcendental equation in phi 2 and phi 3. So, it is not easy to solve that, but we can use this to solve it geometrically, because if you look at this is like a loop closure equation. You look at phi 2 and phi 3 as rotation operators, okay, e power I phi 2 and e power I phi 3. Remember we have been using that as rotation operators all along. So, one way to solve this is if you consider d1 vector and assume that d2 and d3 are pinned to this, okay, on either ends of this. Okay, so, say this is d2, sorry. This is d2 and say this is d3. Then essentially what I am trying to find is how do I, through what angle should I rotate these two. Okay. Say this is phi 2, this is phi 3. Through what angle do I rotate these two so that they meet and form this closed loop. Okay. So, if this is d2, this is d2 e power I phi 2, this is d3 e power I phi 3. So, I can find, so in MATLAB or something, if with the mapping toolbox you can basically find, you know, the lengths of these two vectors d2 and d3. So, that will be one solution. The other solution would be when they meet on this side. I should not call this P2, let me call this Q1 and Q2. Okay. So, this becomes phi 3 tilde, let me call that, this is phi 2 tilde. So, I will have a phi 2 and a phi 3, a phi 2 tilde and a phi 3 tilde, two solutions such that these will meet and satisfy the compatibility equation. So, when you solve this, so that is why it is easier for, so when you are looking at it as a rotation operator, the actual signs will come out when you solve the equation. So, when the rotation, you know, if you do it as, you will see that phi 3 will be a negative sign indicating it is a clockwise rotation. Okay. When you actually solve a problem with this thing, I want you to just understand the geometry of this, what we are trying to do here, because it is otherwise rather difficult, otherwise you would have to expand it. See, d1, d2, d3 are also complex. Okay. So, it is not like your loop closure equation for the 4 bar or something like that, where you have real numbers multiplied by this. So, you have complex times complex numbers. So, then you would have to then separate out, expand this, then separate out the real and imaginary parts, then eliminate one of the angles using the same thing, you know, cos and sine you square and add, but it becomes a very tedious procedure. This basically gives you an idea of what we are trying to do. We are trying to find the two intersections such that this compatibility equation will be solved. One of these, of course, if you look at the form of the equation itself, one solution becomes obvious. What is that? If phi 2 equal to gamma 2, phi 3 equal to gamma 3. That is the trivial solution which will satisfy this compatibility equation. So, you have one solution right there, because you have two columns of the determinant, they become equal, your determinant is 0. Okay. So, that becomes the trivial solution. So, this is the way that if you specify the fixed pivot, you can now solve. So, once you have phi 2, phi 3, you can plug that back into two of these equations. Okay, you take the first two equations, okay, and then you can solve for Z1 and Z2, because now you know the phi 2 and phi 3 that will satisfy the compatibility conditions. So, you cannot assume them as free choices here. You have already assumed your free choice in locating your fixed pivot R1. Okay. So, now phi 2 and phi 3 only if they satisfy a certain condition, you can meet all three, you can satisfy all three equations. Okay. So, that is the synthesis when you have a specified fixed pivot. You specify the fixed pivot by means of, so minus R1 is your specified fixed pivot with respect to your coordinate system. Okay. So, this is the way you would use the dyad method to solve for a specified fixed pivot, design a 4 bar full. Okay. Okay. So, now this dyad method can be used also for linkages with multiple loops. Obviously, you can see that it is fairly easy to extend, you know, you are only looking at. So, if I have a 6 bar, you know, I can again set up the equations for multiple loops and then solve for them for the conditions that I am specified. We will just do the case for a Stephenson mechanism. 4 bar, see a Watt 4 bar is fairly straightforward, it is a 4 bar driving a 4 bar. So, it is fairly straightforward. Let us look at a Stephenson instead and see how we would use this dyad method, how you would extend this to multi-loop mechanisms. In many cases a 4 bar may be sufficient for your application, but as you have more number of positions, one of the ways to deal with it is to go to perhaps a 6 bar. You may have more choices in solutions. You know that with the 4 bar you kind of hit the wall once you go to, I mean it becomes more difficult, and we will see how we will look at the solution for the 4 position synthesis to give you an idea of the solution procedure, analytical procedure for the 4 position synthesis. But when you go to the 5 position, it is even harder to find solutions, because you only have a very limited number of solutions. So, in those cases going to a multiple loop linkage like a 6 bar or higher can actually give you more options for your solutions, and that is one of the reasons. So, we will look at the case of a Stephenson linkage. What we call a multi-loop. Okay. So, So, you can see here, how do you know this is a Stephenson and not a Watt?
There is a binary between the two.
Binary between the two ternary. So, this is a ternary link, fixed link is a ternary link, you have a binary link between the two ternary links. Okay. Again it is a single degree of freedom linkage, and you have this coupler point driving this other diode. Okay. If depending on which one is your input, or so let us say this is my point P1. Okay. So, this that is one diode. Okay. Then I will take Z3, Z4 as another diode, and Z5, Z6, and I will take this as Z7. Okay. And say this is the point of interest, coupler point of interest, whose location, and say this is undergoes gamma, we call this angular motion of this one as phi, this one theta, this one is psi. And then if I have say this is location of P1, or I can just choose, and then from here, so in another position this, so if I call this point P1 as this, or P1 dash, this is P2 dash, then I have this is P2. So, this is my delta 2, not too bad. This should only, sorry, this is only delta 2, this is not delta 2 dash. So, I can write the equations. So, let me take first loop 1, Z1, Z2, this, so I will take this loop with Z1 and Z2. Okay. So, it is in my standard form, right. If I take Z1, Z2, this is Z1 e power I phi 2 or phi j, yeah, I should just call it j. Okay. So, let me take the first loop, and I can write this as, I can write it in the standard form as Z1 e power I phi j minus 1 plus Z2 e power I gamma j minus 1 equal to delta j. Okay. This is loop 1. This is in the standard form. Now, the other two loops, let us say I write loop 2 with Z3 and Z4. Z7 will also come into the equation. So, I have Z3, okay, I can let me just write out the loop once and then. So, I have Z3 plus Z4 minus Z7, okay, plus delta j minus Z7 e power I gamma j, okay, this one, sorry, it should be plus Z, because I am now going, this is Z7, yeah, then I need to designate an angle for this one. Let me call this beta. Okay. For this coupler plane, the angle is beta. Okay. So, Z4, Z6 will rotate by the angle beta. So, I have okay, Z3 plus Z4. I am looking at the loop with Z3, Z4, this is minus Z7, okay, plus delta j plus Z7 e power I gamma j minus Z4 e power I beta j minus Z3 e power I theta j equal to 0. That is the loop. Yes? Minus? I am going this way, no? Delta j is defined like this. So, I am going this, Z7 is minus, I am going along delta j the way it is defined, then this is opposite, sorry, this is along the way that Z7 is defined, etc. So, if I take that to the other side, I can write this as Z3 e power I theta. So, I take everything else but delta j to the other side, then you will get that form. Okay. So, Z3 e power I theta j minus 1 plus Z4 e power I beta j minus 1. Okay. Minus Z7 e power I gamma j minus 1 equal to delta j. Why is? So, Z7, so you will see that, because when I will now take it, say I can take it in any direction that I want, it really does not matter. This is just so it gives a nice form for this equation, okay, because I am defining Z7 from this point P1. See, P1 is specified. So, what I am going to do is actually take that as a free choice, so that I can define the shape of the coupler plane. I can, because I know P1. See, these are things that I need to synthesize. So, I can kind of determine the shape of the linkage by varying Z7. I am going to take that as a free choice. So, for that reason, and it will, so when I move this to the other side, for this loop I get Z3 e power I theta j minus 1 plus Z4 e power I beta j minus 1 equal to delta j plus Z7 e power I gamma j minus 1. what is this? Delta j plus z7 e power. If I look at this vector, if I look at this loop, okay, I can call p1 dash to pj dash as delta j dash, okay, this in this direction. Minus z7, okay, plus delta j plus z7 e power I gamma j. This is nothing but delta j dash in this. See that? It is the displacement of that point p1 dash. Okay. So, now what happens to my equation? If I pick z7, okay, I know gamma j. So, if it is a motion generation problem, say I am given, I know the locations of p1 or the delta j's and I know the gamma j's, the orientation of this thing. Okay. Now, if I choose z7 as a free choice, this becomes known. This equation is not, this is not in standard form up to this point. Okay. This loop, the loop equation for loop 2 is not in standard form. However, if I choose z7 as a free choice, okay, then this becomes in the standard form because the displacement of this becomes defined. Okay. Now, this is just a 4 bar with delta j dash as my displacement vector. So, for loop 3 similarly, I can now write it as, let us do that. So, I have loop 1, I have the first equation. So, I have loop 1 z1 e power I phi j, sorry not, yeah, minus 1 plus z2 into e power I gamma j minus 1 equal to delta j. Loop 2 now, if I choose z7 as a free choice, okay, if I choose z7, then I have z3 e power I theta j minus 1 plus z4 e power I beta j minus 1 equal to delta j dash, where delta j dash is delta j plus z7 e power I gamma j minus 1. Okay. So, this again comes to, and then loop 3 in turn becomes z5 e power I psi j minus 1 plus z6 e power I again beta j minus 1 equal to delta j dash. All in standard form. Choosing z7 gives me lots of options now. Okay. Then I can, after I choose z7, I get these three dyad equations, and then I have free choices in them depending on the number of positions. So, you can see that my number of infinities of solutions starts expanding. Okay. The other advantage is I can now synthesize simultaneously for function generation and motion generation. So, I can do this diet for motion generation and also link theta j and psi j for instance. Okay, so, I get more options. Even more important, see we never talked about motion generation with prescribed timing, although you would think that is important, right. See, we talked about path generation with prescribed timing, where the path of the point and you can coordinate that with the input motion. But with motion generation we did not really talk about that, because already you have another angle that needs to be specified. So, your problem becomes too constrained. Here I can do that. I can link the motion generation to the input timing of one of the angles. So, I can actually do motion generation with prescribed timing. So, I can reach a point and a specific orientation in the plane and coordinate that with the input angle, which I could not do with just a 4 bar. So, going to a 6 bar offers me more options, and you can see that I can extend the diode synthesis. I can extend it to other multi loop mechanisms, not just a 6 bar, I can go higher. Okay. It gives me options for more numbers of solutions. Of course, the trade off is you have a more complex mechanism, it is going to take up more space, it is not as simple as a 4 bar, always trade offs in design, but you can do more with a 6 bar. That is what I wanted to convey to you. And you can now all 3 equations for the 3 loops are in standard form once you pick Z7, and the choices that you have for Z7 give you varieties of solutions for this, because delta j dash is not specified, that is something now you can play with in the equations. Okay. So, that is how you extend the diode form of synthesis to multi loop equations.